Let's start with a bold claim. Scientists at the University of California, Irvine have just stumbled upon something that could reshape how we think about computers, energy efficiency, and even the survival of technology in deep space. It's not just a minor tweak or a cool material trick. This is the discovery of a completely new phase of matter. To put it in perspective, think of how water exists in three familiar phases: liquid, ice, and vapor. Now imagine that, after thousands of years of studying water, someone suddenly discovered a fourth state no one had ever seen before. That's how big this is in the world of quantum physics. The UC Irvine team, led by physics and astronomy professor Luis A. Jauregui, managed to measure something that, until now, only existed in theoretical predictions. The state they observed is so strange that it breaks away from how electrons and holes, those tiny carriers of charge inside a material, usually behave. Instead of doing the opposite of each other, like partners in a dance, these particles begin rotating in the same direction. That synchronized spin gives rise to what scientists are calling a new quantum phase of matter. At its heart, this exotic state is built on excitons, pairs of electrons and holes bound together. Excitons aren't new. Physicists have been studying them for decades. But the twist here is the way these pairs self-organize into something fluid-like, as if they're forming a collective, synchronized quantum soup. Jauregui explains it with a striking image. If we could hold it in our hands, it would glow a bright, high-frequency light. In other words, it's not just invisible math or theory. It has physical properties that are tangible. If only we could stabilize it outside extreme lab conditions. But how did the team actually discover this? The story begins with a special material, hafnium pentatelluride. It's not a household name, but in the world of condensed matter physics, it's one of those layered compounds that can be engineered to display fascinating electronic behaviors. UC Irvine postdoctoral researcher Jinyu Liu, the first author of the study, carefully prepared this material for testing. Then came the real challenge, creating the right environment for the quantum phase to reveal itself. For that, the team went to the Los Alamos National Laboratory, LANL, in New Mexico. There, they had access to some of the world's strongest magnetic fields. To put numbers on it, the researchers exposed a sample to magnetic fields as strong as 70 teslas. If you're not familiar with teslas, here's a scale. The magnet on your fridge is about 0.1 Tesla. The most powerful MRI scanners in hospitals usually go up to 3 Teslas. At LANL, they pushed the limit to 70 Teslas, a force thousands of times stronger than everyday magnets. Under those conditions, the material behaved in a way no one expected. Suddenly, its ability to conduct electricity dropped sharply. That sharp change was the smoking gun. The material had transformed into this exotic quantum state. To a physicist, such a dramatic shift under extreme conditions is a clear signal that something fundamental is happening. And here's where it gets even more exciting. Unlike normal materials used in electronics, this new phase appears to be radiation resistant. That's not just an interesting quirk, it's a potential game changer for technology in space. Radiation in space is brutal. Beyond Earth's protective magnetic field, high-energy cosmic rays and solar particles bombard everything. Conventional electronics degrade quickly under that constant assault. That's one of the reasons space agencies and companies like NASA or SpaceX have to spend billions on radiation-hardened components. But here comes this new quantum state, naturally resistant to radiation. Imagine computers that don't glitch or die in space, even after years of exposure. That's exactly what Jauregui is hinting at when he says, if you want computers in space that are going to last, this is one way to make that happen. Let's pause for a moment to reflect. We're talking about a material that could survive Mars missions or even deep space exploration without needing constant replacement or shielding. And that's only one application. On Earth, the implications are equally stunning. Most of our electronics today rely on the movement of electrical charge, electrons flowing through wires and circuits. But this new phase opens the door to using spin, a quantum property of particles, rather than charge. That's the idea behind spintronics, a field that has been gaining momentum over the last 2 decades. Spintronics could potentially slash the energy costs of computing. Today, about 1% of global electricity goes to powering data centers. By 2030, Estimates suggest this could climb to 8% or more if nothing changes. That's a huge burden on global energy resources. Spin-based electronics could dramatically cut that consumption. And now, with this discovery, the possibility becomes much more realistic. Jauregui emphasizes, this discovery is important because it may allow signals to be carried by spin rather than electrical charge. Think about that. We might one day have computers that not only run faster and cooler, but also recharge themselves, using the very dynamics of these exotic exciton fluids. That's not science fiction. It's a logical next step if researchers can stabilize and harness this state. But what makes this so tricky is that it only appears under very specific conditions right now. Remember the 70 Tesla magnetic field? That's not something you casually install in your living room. In fact, those kinds of fields can only be produced in specialized labs. So, the next big challenge is finding ways to stabilize this quantum phase under more practical conditions. That could mean tweaking the material, changing the temperature, or engineering new compounds altogether. And this isn't without precedent. Think back to the discovery of superconductivity in 1911. At first, it only happened at temperatures close to absolute zero. It took decades before scientists could find high-temperature superconductors that worked at more manageable levels. The same could happen here. What looks like a fragile lab curiosity today might power the world's quantum devices tomorrow. Another fascinating piece of this puzzle is the light-emitting property. Jauregui said the phase would glow a bright, high-frequency light if we could hold it. That implies potential uses in photonics, the science of controlling light for communications and computing. Imagine using this material to send signals not through wires, but as pulses of light immune to noise and degradation. Fiber optics already transformed the internet. This could push it to the next level, where information is transmitted faster and more efficiently than ever. And if you think this is only for future supercomputers, think again. Everyday devices, phones, laptops, even electric cars, could benefit from components that run cooler, faster, and longer. Let's not forget the resilience to radiation. On Earth, that could mean electronics in nuclear plants or high-radiation environments could survive where current tech fails. The possibilities keep branching out. Now, some of you might wonder, how unique is this discovery? Are we sure it's not just another version of a known phase? That's exactly why this result made it into Physical Review Letters, one of the most respected journals in physics. Peer review confirmed that what the UC Irvine team measured is genuinely new. And it's not a small tweak. It's a fundamentally different quantum organization of matter. That's rare. In fact, most phases of matter we deal with, solids, liquids, gases, plasmas, have been known for centuries. New ones don't come along every day. But in the last 2 decades, exotic states like Bose-Einstein condensates, time crystals, and now this exciton fluid are expanding the landscape of physics. And each time, the discoveries aren't just academic. They ripple out into technology. The transistor, the foundation of modern electronics, came from studying semiconductors in the mid-20th century. The laser came from quantum optics. Who's to say this new phase won't give rise to the next wave of technology? Let's circle back to space for a moment. SpaceX, Blue Origin, NASA, all are investing heavily in long-duration missions. Sending humans to Mars is no longer just a dream. It's on the planning boards. But one of the major hurdles is technology survival. Computers, sensors, communication systems all need to endure years of cosmic radiation. This discovery could offer exactly the kind of breakthrough needed to make those missions feasible. Instead of shielding computers with heavy, expensive materials, what if the computers themselves were radiation-proof? That could reduce spacecraft weight, cost, and complexity. In space travel, every kilogram saved counts. Suddenly, this discovery isn't just about physics, it's about enabling humanity's push into the cosmos. Of course, there's still many unknowns. Jauregui himself admits, we don't know yet what possibilities will open as a result. And that's the thrilling part. This is a door that has just been cracked open. Behind it lies a landscape we can't fully see yet. But we know it's there. And we know it's different from anything we've seen before. For now, the focus will be on replicating and studying this state in more detail. Other labs will attempt to verify the results, test different materials, and look for practical conditions where the phase can exist. Some will try to probe its optical properties. Others will explore its resilience to different forms of radiation. And still others will ask the big question, can this be scaled into a working device? That's the beauty of science. It builds step by step. What starts as a strange lab result can eventually power revolutions. Just as the electron itself was once a curiosity, now it runs the world. The same may one day be said about this quantum phase. Imagine kids in the future reading about this discovery in their school books the way we read about the Wright brothers' first flight. For now, though, let's ground ourselves in what we know. UC Irvine scientists engineered hafnium pentatelluride. They exposed it to 70 Tesla magnetic fields at Los Alamos. The material's electrical conductivity suddenly dropped. That drop signaled the formation of a new excitonic fluid-like state. Both electrons and holes rotated in the same direction, a never-before-seen arrangement. The phase could glow bright light if stabilized. It carries signals via spin rather than charge. It resists radiation naturally. All of that adds up to an extraordinary discovery. And while it may sound futuristic, the fact that it's already been measured is huge. Theoretical predictions becoming experimental reality is the gold standard of physics. It means we're not just dreaming, we're observing. From here, the journey is about turning observation into application. And that's where collaborations between physicists, engineers, and technology companies will come in. NASA, SpaceX, and DARPA could all have an interest in funding follow-up work. So might companies chasing energy-efficient computing here on Earth. The race to harness this new state could begin faster than we think. Remember how fast graphene went from a lab curiosity in 2004 to an entire field of applied research? This could follow a similar trajectory. And the stakes are high. Whoever masters this first could control the next generation of computing and space technology. Still, it's important to temper excitement with patience. Physics breakthroughs often take decades to filter into consumer technology. But the spark has been lit. And once a spark is lit, history shows that innovation follows. Whether it's superconductors, lasers, or semiconductors, the timeline is long but inevitable. So let's appreciate the magnitude of what UC Irvine has accomplished. They didn't just find an interesting quirk. They revealed a new phase of quantum matter, something no one had ever seen before, something that could resist radiation, carry signals through spin, and glow with its own high-frequency light. In the process, they've given us a glimpse of what the future of technology could look like. Computers that last decades in deep space, devices that recharge themselves, data centers that consume a fraction of today's electricity, communication systems that run on light itself. It all starts with excitons, spins, and a little piece of hafnium pentatelluride under a massive magnetic field. From that seed, the future may grow. As Yoregi says, we don't yet know all the possibilities. But we do know this: the quantum world has once again surprised us. And the journey ahead looks brighter than ever. If you enjoyed this video, subscribe now and stay tuned for more groundbreaking stories from science.